So hello everyone, this is lecture 30 for the solid state physics, in which we were studying about the band theory and it is almost completed. Now we were discussing some questions. So I have given you these questions as homework. So hope you try to prove these, but many of you didn't make it because let me tell you why. First, for BCC structure, how can you prove this? So for BCC structure, you know how it will look. Means you will get this type of structure. Something means in the center you will have an atom, then at the corners you will have the neighboring atoms. So it will be 8 neighboring atoms this atom will have. So now, as we did in the SCC simple cubic, there were 6, so we did in the coordinates of all 6. So same we will write the coordinates of all the 8. So it will become like this. Okay, then we will substitute in this equation for the tide binding approximation. And this we put every this position vector here, all of the 8, and for the in place of k there will be kx, ky, kz, I cap, j cap, k cap. Then after you multiply them and you find the sum of all these terms, you'll get something like this: e to the I kx a by 2, ky a by 2, kz a by 2, then kx a by 2. You will get 4 terms this positive and 4 minus terms of e to the power minus kx. Same for the not 4, yes, 4 terms. Okay, so then you will take them in the pairs and then you will find the cos. You can write them as e to the power kx a by 2 plus e to the power I minus kx by 2 divided by 2. Then it will give you cos kx a by 2. That's how you can solve this. Means it will be a very long procedure, so try to avoid. Means it will be no need in the question paper or the exams. So here just you need to remember, for BCC structure we will have this dispersion relation. Which one? This one. Okay, it is multiplication. Okay, cos kx by 2, cos ky by 2, and cos kz a by 2. Okay, multiplication of all these 3. Now for the FCC structure, there will be 12 neighboring atoms. Means let me show you something you can visualize. Means in the FCC structure you will have atoms in all the faces. So if you find the neighboring atoms of this atom, then it will be on all these 4 faces, on all these 4 faces, and all these 4 faces also. Okay, this and this means 1 2 3 4 5 6 7 8 and 9 10 11 12. So you will have 12 neighboring atoms here. Then you will write the coordinates of all these 12 like this. Then you will again use the tide binding approximation and you will substitute the values and find the summation. Then after solving, don't need to solve, just remember this result for the FCC. It is cos kx a by 2, cos ky a by 2, cos ky a by 2, then cos kz a by 2, cos kz a by 2, and cos kx a by 2. Just remember these results, very important. Question can be asked directly. So now you can solve these questions just same as we did for the simple cubic. Means for long wavelength k tends to 0, so this cos kx by 2 will turn out to be 1 minus 1 upon 2 kx by 2 ka whole square. And same for this, same for this. Then you can find these group velocity and the component velocity by, it is 1 upon h cut del E by del kx. So you can solve this. Okay, just that 1 minus kx square by 2, and the same as in the simple cubic we did. For these velocities you can find 1 upon h cut del E by del kx with respect to kx, then with respect to ky, then kz. Then all the components will give you group velocity under root vx square plus vy square plus vz square. Then you will get in terms of kx, ky, kz, then substitute these values and you will get the different group velocities at these components. Then you can find the at bottom and top. So first for the bottom, when k equal to 0, then the minus of this will give you top, the effective mass. Then find the tensor matrix, and bandwidth is nothing but just difference between the top and the bottom energy at these points. Okay, so use these equations for all of them. you can just do the same procedure as we did in the FCC. Oh, sorry, SCC, simple cubic structure. Okay. Now there is one more thing. It can also be asked in the questions. So Fermi sphere, as we discussed about the Fermi radius in the free electron theory. Then as we know the Fermi radius, so that radius can form the sphere also. So that's why we call that sphere as Fermi sphere. So along kx it is k, along x it is kx, along ky, and then along z it is kz. And at when energy is Fermi energy EF, then we will have the electron energy as kBt, and this temperature is Fermi temperature. And what is the energy? Energy is nothing but h cut square, kf square divided by 2m, and kf is Fermi radius. We already discussed these. If you see the previous lecture about the formula for kf and all these things. Okay. Now what was the kf? Kf is sum of all these components, kx, ky, kz. Then kf square will be given by kf square plus ky square plus kz square. So see, this equation is equation of a sphere, where kf denotes the Fermi radius. You can compare with this equation. This is the equation of a sphere in the real space, but this is the equation of a sphere in the reciprocal space. So you will understand the reciprocal space when we discuss the crystals, the crystallography. You will understand that we have everything in the reciprocal space also as in the real space. So reciprocal space is nothing but this is 1 upon this length. Okay, so we know this is 2 pi by lambda type, so that's why it is in the reciprocal space, the equation of a sphere. So just remember it as it is. We will study about it more in the crystallography. That will be our last topic for solid state physics. Now what kind of question can be asked? So find radius of Fermi sphere in simple cubic and BCC and FCC. For monovalence atom, means valency is 1. So we know the formula for the Fermi radius, that is 3 pi square n by to the power 1 by upon 3. We already find it this when we discussed about the Fermi energy and all. Then Fermi temperature, Fermi momentum, Fermi velocity, we already discussed these terms. So this was the direct formula, where n is the concentration of electrons. So it can be found as n effective divided by V. N effective is number of atoms in a unit cell. This is volume of a unit cell. This is valency on each atom. So it is 1 for monovalence atom. So it will be number of atoms. It is for simple cubic it will be 1. For BCC it will be 2. For FCC it will be 4. Okay. So and it will be A cube always. So just substitute here. And we will get as these. So for simple cubic it is 1, so 3 pi square divided by a cube 1 by 3. So this will be our Fermi radius. For BCC this will be Fermi radius. For FCC this will be Fermi radius. Now question can be asked like this: check whether Fermi sphere lies inside the first Brillouin zone or not in simple cubic. So we need to check if Fermi sphere lies inside or not in the Brillouin zone. Okay, for a simple cubic. So for simple cubic we know this Fermi radius is what is the Fermi radius for the first Brillouin zone? Sorry, not first Brillouin zone. For simple cubic, this is our Fermi radius. Okay, and we will check if the volume of this cube is what? This side cube. So how you can find the side? Means it is pi by a here, pi by a here. Okay. Then pi by a minus this, so it will be 2 pi by a. So 2 pi by a cube will give you the volume. Okay, so this is nothing but first Brillouin zone, this pi by n minus pi by a. So how can we check if this Fermi sphere lies inside or outside? So first Brillouin zone will be this. Now check the radius, if that is greater or less than this 0 to pi by a. If it is greater than this, then sphere will be lies outside. If it is less than this, then sphere will be lies inside. Okay, so let's check. What will be the Fermi radius for simple cubic? This 3 pi square by a cube 1 upon 3. So we have to compare this with the pi by a, this length pi by a. So if it is less than this, so it will be lies inside. So how can we check if it is less or greater? So just multiply with pi up and down. So it will give pi cube will turn out to be pi because of 1 upon 3. And 3 to the power 1 upon 3 will give you 1.4 something. And if it will be 1 pi extra, then it will give you pi by a outside, and it will be pi up and down, so pi 1 upon 3. Now we have to check this value of this. So this value will be came out less than 1. Okay, and if it is less than 1, then definitely this whole term is less than pi by a. So we'll say that Fermi sphere lies inside the first brilliant zone. Okay, now there is this kind of question can also be asked. Find n such that Fermi sphere just touch the first brilliant zone. So we need to find this n, the concentration of electrons if first billion means first जो हमारा वो है Fermi sphere, it touches the first brilliant zone. So Fermi sphere, so radius will be kf, and if it is just touching this, so this radius should be equal to pi by a. So we'll just substitute the values. Kf equal to pi by a, and for kf it will be 3 pi square n and pi by a cube. Why? Because here it was 1/3, so it will give here it will become cube. Okay, now from this equation we can find the n directly. Okay, and if we have n, then we also can find this number of atoms in a unit cell also. So we can find many things from these equations. Just remember these relation. And now I have a question for you, try to solve it. Otherwise you will solve it after the crystallography, then you will have a better understanding about it. In 2D lattice, a equal to this angstrom, b is equal to this angstrom. So this is a 2D lattice. Find the Fermi radius in this 2D lattice and first brilliant zone in this 2D lattice. Then check whether Fermi circle lies within first brilliant zone or not. Okay, so you need to check this. So for that you need to understand that how we draw the brilliant zone in the 2D lattice. So you will learn about it later. Then you have to find a Fermi radius in 2D lattice. So you can find the Fermi radius after that only. So try to solve it if you know these concepts, and I will tell you later about this. Then next in the next lecture we will start with the crystallography. That will be our last topic for the solid state physics. Then this will be ended. Okay, thank you guys.